the graphical models framework and how it's set up, and some basic background and theorems about the how Markov equivalence class works, how the do calculus works, those sorts of things. Today, we want to find out a little bit more about where the graph comes from in the first place. So how can we discover causal relations directly from data? And I'm delighted to have Dan Malinsky do this for today. We'll have the same setup as we had yesterday. We'll have 4 lectures over the day. We'll go for an hour now, have a coffee break, then a 2-hour lunch break after the second hour, and then 2 sessions in the afternoon again. I think brief interruptions for clarification questions are good, right? So please engage there, and I will try and keep track of the questions on Zoom for those of you who are on Zoom. In any case, please help me welcome Dan Malinsky. He's professor of biostatistics at Columbia. Thanks for doing this.
Hello. Is this microphone working? Yes? Okay. Let me know if you can't hear me at any point, if I should just speak louder or repeat anything. Thanks a lot to Frederick and the other organizers for putting this together. It's been really great so far, and for inviting me to participate. So the lectures today will be a kind of broad overview of a pretty large research area, causal discovery, which is also sometimes called causal structure learning, because you're learning the structure of a graph, or causal model selection, because you're selecting a causal model, or sometimes causal search, because you're searching for a causal model. These are all synonyms for the same thing, which is learning a graph from data somehow, or possibly a set of graphs. And as any kind of like broad introduction to a big research topic, it's going to be somewhat biased towards, you know, my perspective on things and my interests. And I won't be able to get to obviously everything that is cool about causal discovery, even in 4 hours. But hopefully we'll give you a kind of flavor of what's going on in this area, introduce you to the main kind of concepts that will help you do research in this area if you so choose. So yesterday, as Frederick said, the lectures yesterday were from the perspective of having been given a graphical model, how do you do something with it? So the kind of tasks that you were learning about yesterday was mostly the task of deciding identifiability of causal quantities or interventional distributions. And there's other tasks that you might do given a graph, and people will go into that later. But a question, an obvious question that arises is, where does the graph come from? And there's many different sources. So a common source of information that might lead you to posit some graph to represent your situation is the experimental design or problem design of some study that you are engaging in, for example, a randomized controlled trial or some sort of longitudinal trial or something like that. But there's plenty of scientific questions for which a carefully designed experiment is not possible or feasible or obvious. There are instances where background theory, whether that's biological theory or economic theory or theory about the structure of the brain or genetic regulatory networks, may help you specify a graph, or at least part of the graph. But theory, of course, may be wrong. And sometimes we want to test whether our theory actually matches reality. Theory may also, especially in this kind of age of high dimensional data, big data, theory may be underspecified. It might tell you how some things are related to each other, but it might not tell you how everything is related to everything else. And experts who may be drawing on some combination of theory and other background knowledge may be a source of information. But of course, experts may be wrong. Experts may disagree with each other, or the problem may be kind of intractable in high dimensional settings for expert opinion. So the kind of remaining option that we focus on today is how to learn something about the graph from data. And the question is how. So there's different strategies or kind of categories of approaches to causal discovery, some of which we'll talk about today. Constraint-based learning, score-based learning, semi-parametric methods, optimization-based methods, and hybrid methods. This is kind of how I would carve up the space of possibilities in causal discovery, although there's definitely algorithms that don't fit in nicely into any of these categories. For this first lecture this morning, we're going to talk mostly about the first two, constraint-based learning and score-based learning, and specifically kind of two classical algorithms that I would say kind of define the paradigms that those are, the constraint-based and score-based paradigms. So score-based approaches, constraint-based approaches typically proceed by testing of conditional independence constraints. So different graphs will imply potentially different conditional independence constraints on the observed data distribution. And constraint-based methods are kind of the most direct in the sense that they just test those constraints and try and infer backwards to the graph that might have generated the data. And the classic example is the PC algorithm, which we'll talk about today. PC stands for Peter and Clark, Peter Spurdes and Clark Gleamore, who proposed the algorithm or early version of the algorithm in the early 90s and has been improved in various ways since then. And the score-based approach, instead of testing constraints, it operates on the basis of optimization of some sort of measure of model fit or a score that assigns for each graph some number, which is supposed to be, better or higher number for graphs that fit the data more well, and a lower number for graphs that fit the data less well. And the kind of paradigmatic greedy optimization of the model fit score is this algorithm, the greedy equivalence search, GES, which is another procedure that we'll talk about. So as the kind of background notation, what I'll use in this talk, I'm going to use the calligraphic G for a graph. There'll be different kinds of graphs we'll talk about throughout the day with vertices V and edges E. And there's going to be P vertices. And corresponding to those vertices is going to be a random vector, also of length P. And I'm going to use the letter X to denote that random vector. And it's going to be assumed to be defined with respect to some background, common background probability space. And the induced joint distribution or density of X will be generically denoted P of X. Okay?
That's a bit.
What can I help clarify? Yeah, well, you should know that I guess look out for when it's P of X, that it's a distribution, P of something. Yes. And to make things more confusing, I prefer to keep the vertices of a graph and the elements of a random vector separate when I can, but it's kind of annoying for the purposes of a long presentation. So I won't typically carefully distinguish between the vertices of a graph and the random variables. I'll just kind of say V equals X when it's convenient. And I'll use these sets, which will kind of have their obvious definitions related to what you learned yesterday. I'll talk about like the parents of X in a graph G, the adjacencies of X, which could be, they're connected by an edge in either direction, the ancestors of X, the descendants of X, and so forth with respect to a graph G. And I'll use this symbol, the perpendicular symbol with D, to denote D separation in a graph, and this one to denote the conditional independence relationship. So D separation is something about pathways in a graph, which you learned yesterday, and conditional independence is something about how a joint distribution factorizes, right? And another note I'll say is that throughout I'm going to make reference to this distribution P of X that's induced by some causal graph G. And in the lecture yesterday, you heard about causal graphs explicated in terms of systems of structural equations, SEMs or SCMs. And in a later lecture tomorrow by Thomas Richardson, you'll hear about causal graphical models from the perspective of potential outcomes. And I just want to say that everything that I'll talk about, at least in this morning, is fine regardless of which formalism you adopt, whether you think of the causal graph in terms of a system of equations or in terms of a potential outcomes model. Nothing makes a difference for what we'll talk about here. And in this lecture in the morning, I will assume this kind of major simplifying assumption called causal sufficiency. And I'll relax that assumption in the latter half of this lecture in this afternoon. But for the purposes of this morning, we're going to assume that there are no unmeasured, no hidden, no latent variables that act as common causes of multiple of the measured variables in our data set. So meaning that our variables X that we have access to, that we have data on, are sufficient to talk about the causal relationships among members of X. That's a major assumption that is clearly violated in most application areas. And we will relax that assumption as we go on, but it's kind of easier to get started thinking about graphs over X than graphs over this kind of larger space of possibly unmeasured and hidden variables. And we're also going to assume all day that the data generating process contains no feedback, so it's recursive, meaning that the graphical representation has no cycles. So with those two assumptions, what that means is that we're assuming that the data generating process corresponds to some directed acyclic graph, acyclic meaning it has no cycles, with vertices corresponding only to the members of X. And in part 2, we'll relax this. Any questions about that before I go on? Okay. So if you consider a given DAG G, we learned yesterday that there's this Markov property, which is sometimes called the global Markov property, that is a relation between d-separations in the graph and conditional independencies in the implied distribution, in the induced distribution. So if xi and xj are d-separated given some xs, then they're conditionally independent in the distribution induced by that graphical model. So here xi and j are just generic members of X, and xs is some subset of the remaining variables. Yes?
Quick question from Zoom. What's the problem with cycles in the graph?
The problem with cycles in the graph is that it just makes things more complicated. So there are methods that do causal discovery in settings that have cycles, but a lot of these properties that, like this one, for example, and ones that we will discuss later, kind of break down when you start allowing for cyclic graphical models, at least when you try and be non-parametric with them. In kind of special cases, if you talk about cyclic models that are linear, then nice properties work out. But in the general case, cyclic models introduce a lot of complications. They make d-separation more kind of complicated. They make Markov equivalence kind of more complicated. And so I'm just not going to get into it here.
Following up on that, couldn't you just unroll any cycles into like a time evolving DAG? Like you don't need to have cycles. If you get like variable feedback from xi and xj, you can just roll it over xj, comma 1, xi, comma 2, and just.
Right. So the question is, could you, if you had a cyclic graph, couldn't you just unroll the graph into a kind of acyclic representation over time where things are causing each other over time? Yes and no. There is a lot of work that proceeds in that direction, but it gets also a bit more complicated. So you have to make a decision about the sort of speed at which causality propagates through that kind of system and how it relates to the granularity of the data that you have. So if you have some time series data, for example, are the causal relationships going at a rate such that it doesn't introduce any contemporaneous or kind of cyclic relationships at the level of time t? There's sort of a lot of choices you have to make about how to do that kind of thing properly, and there is work that goes in different directions, yes. But typically, a lot of the times people do like cyclic graphs in a setting where they don't have time series. They just have like equilibrium data. They have snapshot data, say, of concentrations in a cell or something like that, and they want to allow for the possibility that there's feedback that generated the data. Yeah. Okay. So, global Markov property. So this says that d-separation implies conditional independence, and constraint-based learning. So this is what we mean when we say that the graph places a constraint, a conditional independence constraint on the data or on the distribution from which the data is sampled. So the constraint is a conditional independence constraint. It says that if there's this d-separation in the graph, if there's something about pathways in the graph, then xi and xj will be conditionally independent given the set xs. So constraint-based methods directly exploit those implied constraints on P of X to try and infer backwards from the data to the graphical structure that generated the data by a sequence of tests, testing those conditional independence constraints directly. Score-based methods, on the other hand, proceed by assigning to every graph G some measure of how well the graph fits the data. And that measure is going to be something which basically says how many or to what degree are those conditional independence constraints found in the data itself. And then by scoring different possible graphs, can try and distinguish between which one fits the data better or worse. And so higher scores, so we have to talk a little bit about how to define such a score. But once you define such a score, then higher scores mean a better fit. and a score-based approach can be viewed as an optimization problem of finding the graph that maximizes the score. Okay, neither of these approaches is universally better than the other, but they each have their own virtues and drawbacks depending on the setting, and that's why I'm talking about them both. There are also theoretical connections between these two approaches. You can kind of translate back and forth to some extent between them. And so they are actually not quite so distinct as may seem. And we'll get to that a little bit later too. A fundamental assumption that both typical constraint-based methods and typical score-based methods make is the faithfulness assumption. Faithfulness is really key to causal discovery. And there's kind of strengthenings of the faithfulness assumptions and weakenings of the faithfulness assumptions in various particular proposals, but always like some version of faithfulness is going to arise. The reason is that the Markov property that we just defined is unidirectional. It says deseparation implies conditional independence. But what we do when we test conditional independence from the data is we learn something about a conditional independence fact, and we want to infer towards a deseparation, right? So we want to go from the other direction, from conditional independence to a deseparation. That's not part of the Markov property of graphs. That's an additional, that there is that link in that other direction is a substantive assumption, or you might say a methodological assumption, that we kind of have to make in order to make this kind of procedure work. So to kind of put it in a bit of a slogan, faithfulness assumption, or faithfulness assumptions, generally speaking, are ones that tell you or assume that all observed conditional independence constraints have an origin in the graphical structure, that there's no conditional independence constraints that sort of happen accidentally or for reasons unrelated to the graphical structure. And this puts missing edges in a graph and conditional independence relations in a one-to-one correspondence. But I want to emphasize that this is a substantive assumption on the distribution P of X, and in general is not true. It may be violated, and sometimes you can detect certain violations. So here's an example, a couple examples of where faithfulness is violated. Say I just have these three variables, x1, x2, x3. And this is the DAG, the true DAG that relates them. But I also have this deterministic relationship where x3 is just 2 times x2. It's a deterministic relationship. I know x3 exactly. If you tell me x2, I just multiply it by 2. So by the Markov property, x3 is independent of x1 given x2 because they're deseparated, right? x1 and x3 are deseparated given x2. So that's what follows from the Markov property. But there's this additional independence which follows from the determinism, namely that as long as I know x3, because x3 and x2 are deterministically related, learning x1 no longer is informative. So that's an additional independence constraint which follows from this deterministic relationship that's not implied by the graphical structure. So that's one kind of thing that's ruled out by faithfulness. Another example is what's often referred to as exact cancellations. And this is easiest to see in linear models, although it's not only a thing about linear models. But imagine this graph, x1, x2, x3. This is a complete graph. Every edge is connected to every vertex is connected to every other vertex. And so there are no deseparations that hold in this graph. There's no conditional independencies that are implied among x1, x2, x3. But if I posit a linear structural equation model that corresponds to this graph, and I choose my coefficients in such a way that they cancel out upon substituting the definition of x2, which is here alpha times x1, will be alpha beta x1 minus alpha beta x1. X1 will drop out of this last equation, right? So that will end up implying, regardless of whatever the epsilons are, as long as they're independent, it'll imply that x3 is independent of x1. That the influence between x1 and x3 that's kind of direct cancels out the influence that's indirect through x2. So that's an independence constraint that follows from this choice of parameters for the structural equation model that is not implied by the graph. And so it's a faithfulness violation. So no independencies follow from the Markov property, but x3 and x1 are independent by exact cancellation. So faithfulness rules out both of those kinds of things. It says that the only conditional independence constraints that I'll observe in the data are the ones that are implied by the graphical structure. It creates a if and only if here between the d-separation relationships and the conditional independence relationships in the distribution for all sets in the set of vertices. Questions? Yes.
So trying to be able to capture this linear structure that you put.
You mean in this example? Yeah, I mean, so the question was, is it possible to rephrase this model somehow with an additional variable? And yeah, that might be possible. But the faithfulness is kind of about the specific set of variables you've chosen to represent the problem. So if I've chosen x1, x2, x3, and this parameterization happens to hold, then that's a faithfulness violation. I can try and expand to a different set of variables if I have data on additional things like some x4. But for a particular choice of variables, that's a faithfulness violation. And I should say there's a large literature on faithfulness. You might say that exact cancellation like this is a priori unlikely to happen out in nature. And there's arguments to the effect of why it is unlikely or why it actually is to be expected in certain contexts. There's a kind of mathematical argument, which is that in linear models with as long as your prior distribution over models is continuous with respect to Lebesgue measure, exact cancellations like this are measure zero. So they're kind of like a priori unlikely in some sense. But you can also imagine that in some settings, the system was designed exactly to act in a way that cancels, that exactly balances things. For example, in like homeostasis in your body or in the thermostat in this room, there's a kind of balancing act in which things are kind of meant to cancel out. And so depends if you like measure theory or homeostasis. I don't know. Okay, so given the faithfulness assumption, we want to learn something about the graphical structure from conditional independences in the data. And an important substructure that arises over and over again in causal discovery are these colliders, which we talked about yesterday, or specifically unshielded colliders, meaning triples of variables in which one variable in the middle has two parents, and those parents themselves are not adjacent. And that's a very special substructure in DAGs. The reason being is that by d-separation, you have a marginal independence. So in this example, I'm like trying to start my car in the morning, and there's two independent things which are sort of related to whether my car is going to start. For example, whether I have fuel in the tank and whether my battery is charged. And sort of like a priori, there's no reason why fuel in the tank and the charge in my battery should be related to each other. They're just kind of independent things. But if I know that my car doesn't start, then the status of battery charged and fuel level become informative about each other. For example, if I know that my car does not start, but that I filled up the tank yesterday, then it must be because my battery is dead. So conditional on some value for car start, my fuel level and battery charge become associated. They become dependent. And thinking about this graphically, that latter half is what follows from the faithfulness assumption. So d-separation just says that there's a d-separation between battery charge and fuel level given the empty set. That there's no deconnecting path given the empty set between them. But if that's the only conditional independence between those three variables, then specifically this conditional dependence must also hold. So, and this is just a general fact about unshielded colliders, is that they have this kind of marginal independence structure, but conditional dependence implication, given faithfulness. This is very different from a kind of similar graph over three variables where I've just made them all go in one direction, which is sometimes called a chain. And in this kind of DAG, we have by d-separation, x1 is not d-separated from x3 because there's a deconnecting path through x2. And by d-separation, x1 is d-separated from x3 given x2. If I block x2, I'll sort of limit the ability of information to flow from x1 to x3. So these chains whether it's going in this direction or going in the other direction, they both imply a deseparation fact, which is that x1 and x3 are deseparated given x2, which is the opposite of what was found in this unshielded collider example. And forks, this kind of setting where one variable is a common cause of two others, has the same set of deseparation relationships as the chain we just saw. That in this graph, x1 and x3 are deconnected, they're not deseparated, conditional on nothing, but they are deseparated if I condition on x2. So in that sense, this chain over three variables just implies the same stuff as this chain over three variables, sorry, chain and fork. So whether it's going from x1 to x2 to x3 or from x2 to x1 and x3 implies the same conditional independence constraints. So this means that colliders, unshielded colliders, act as a sort of smoking gun to determine some substructures or orientations in the graph, whereas forks and chains can lead to some amount of underdetermination. That with just those three variables, I can't distinguish between the fork and the chain, but I can distinguish between unshielded collider and fork or chain. So how might you, so knowing just this stuff, how might you select a model if you've given a set of variables and given some data that you believe was generated from a directed acyclic graph? How might you select a model if computational limitations weren't an issue? Well, one thing you might try and do is just list all the possible DAGs over that set of vertices that you have. This, of course, is impossible if you have like more than 4 or 5 vertices, but for a small number, imagine that it's not too hard. And I can list from each, I can take each graph and derive the conditional independence constraints implied by that graph using deseparation and faithfulness, and just test them. Do a statistical test of this independence hypothesis, and then sort of like one by one say, is this graph rejected? Is this graph rejected? Is this graph rejected? And I'll notice that multiple graphs will imply the same conditional independence constraints, and some graphs will imply different conditional independence constraints. So so if I did it in this kind of setting with these three variables, I can at least determine whether I'm in, this part of the slide, one of these three, if they're all not rejected, or this part of the slide, if that one's not rejected. This is, of course, impossible. So we want a better thing to do, computationally speaking, but it's also kind of inefficient because why should I test these three kind of equivalent graphs, equivalent in the sense of implying the same conditional independence constraints separately if I know that they belong to the same equivalence class? So you learned about Markov equivalence yesterday. And so a better thing to do would be to search in the space of Markov equivalent graphs. So test every graph in the equivalence class just once rather than multiple times. And there's a representation of Markov equivalence classes for DAGs that ends up being helpful, which is called a CP DAG, a completed partial directed acyclic graph, which will basically group those three graphs that imply the same conditional independence constraints, represent them with one structure which has undirected edges, where the undirected edges mean that there is some graph in the equivalence class in which the edge is directed one way, and some graph in the equivalence class where the edge is directed the other way. And so for this equivalence class of three variables, the representation is this undirected graph. And the equivalence class of this structure is just the singleton, it's itself. There's no other graph over three variables that implies that unshielded collider set of conditional independence relationships. And you can generalize this to an arbitrary number of variables. So if I let G be a DAG, then the CP DAG, which I'll call C, completed partial DAG, implied by G is a mixed graph, mixed meaning it has both directed and undirected edges, that has the same adjacencies as G, and a directed edge between xi and xj, if and only if the edge xi to xj is common to all DAGs in the Markov equivalence class, and undirected edges elsewhere. So it's a kind of single structure that includes both directed and undirected edges to represent a set of graphs, a Markov equivalence class. And they're equivalent, again, in the sense that they imply the same conditional independence constraints on the data, or you could say the same d-separations, which is equivalent. Yes?
I missed this, but what is an unshielded collider?
Yeah, good question.
Morality, I think. What we said.
The immorality?
Yeah.
Okay.
Yeah, I think they were called immoralities in the
When
previous.
there's no connection.
So it's when the two colliding variables are not themselves adjacent. Good question. But unshielded collider, immorality, same thing. Yeah.
So rate is not just about learning the direction of the arrows, right? So we only enumerate those points.
Good question. So the question was, in causal discovery, we're not just learning the directions, we're also learning the adjacencies, like which vertices are connected to which others. And we're going to get to a strategy for that in exactly just 1 second. I guess here I was sort of assuming that if I have 3 variables and I sort of all know that they're pairwise dependent in some sense. But really, I want to select like all possible graphs over 3 variables, which includes the empty graph where none of them are connected, or the graph where they only have 1 edge, and so forth. Yeah. So to that point, the kind of more sophisticated search procedure that both takes into account this Markov equivalence thing and tries to be as efficient as possible about which tests to perform will be a procedure that does a sequence of conditional independence tests to search for possible d-separations, basically. And a naive approach would be to consider for every pair of variables that I have, all subsets of the remaining variables, right? So if xi and xj are d-separated by some subset of the remaining variables, it's got to be a subset of this. And so I could look at every such subset and do every such independence test. But that would take too long and require too many independence tests. And eventually, many of those independence tests will have low statistical power. So instead, what we do is we take advantage of some graphical properties, some of which you learned about yesterday. In particular, that it follows from the Dag-Markov properties that if xi and xj are not adjacent, then it must be that they're d-separated given the parents of xi or the parents of xj. So remember, like the parents are sufficient to block all non-descendants. Once I condition on the parents, they'll be independent of all non-descendants. So this is just like this follows from that fact. So that means if we knew the parent sets, we would only need to test this. We don't know the parent sets in advance. That's in part what we're trying to learn. So what the PC algorithm does is it looks at a kind of super graph of the truth at every step, like a graph that has more edges than the true graph by construction, and tests all subsets of the adjacencies of each xi and xj, because the parents must be a subset of the adjacencies. So the idea is that PC starts off with a complete graph where everything is connected to everything else. And it starts off with only undirected edges, because in the first stage is sort of only interested in conditional dependencies. So the complete graph is a super graph of anything, right? Any graph that's the truth, the complete graph is a larger graph than that one. And it selects conditional independence hypotheses to test by looking at every pair of variables, say like x1 and x2 and x2 and x4 and so forth, and testing subsets of the adjacencies of those variables, removing an edge when it finds a conditional independence, because that conditional independence means that they must be d-separated, and that d-separated means there must be some missing edge between them. And in particular, the kind of schedule that PC operates under is that it tries to start off with the kind of easiest conditional independence tests to do, namely marginal independence, where you condition on nothing, or the empty set, and then start conditioning on more and more variables, larger and larger subsets of the adjacencies at every step. So as like a quick schematic, you might start with, you have these 4 variables. You do some independence tests that are marginal, meaning conditional on nothing or conditional on the empty set. And you find this conditional independence holds, that x2 and x3 are independent, conditional on the empty set, so marginally independent. And that leads me to remove the edge between x3 and x2. I do some more marginal independence tests and find, for example, that x2 and x4 are independent, also conditional on the empty set. And that leads me to remove this edge between x2 and x4. then I start testing subsets of the remaining variables, just 1 second, that will get higher and higher in cardinality. So I've tested all the marginal independencies. Now I want to test conditional independencies where I condition on subsets of size 1. So maybe I find that x1 and x3 are independent conditional on x4, which leads me to remove this edge between x1 and x3. And then finally, we're going to use that collider smoking gun that we talked about in order to start orienting some of those edges. So the first step just tests conditional independence and removes edges. And the second step says, if I find this particular pattern in which, remember, x2 and x4 were marginally independent, but they're not conditionally independent when I condition on x1, that leads me to conclude that there's a collider colliding at x1. So that will orient these two edges in that direction. And then remaining undirected edges, after I've done as many conditional independence tests as I can, and I've oriented as many unshielded colliders as I can, there'll be some remaining undirected edges, and those represent or reflect the Markov equivalence. So in particular, this set of conditional independencies I just found is consistent with both x3 going towards x4 and x4 going towards x3. They're in the same Markov equivalence class, and I haven't found any conditional independence constraint to distinguish them. There's a question back there.
This approach does not seem to scale well with a number of large number of variables. Are there any other approaches which is better with the number of variables? So here you have like four variables, but in practice you may have like even 100 or 200 variables. So I'm just wondering if there are like kind of more computation efficient approaches to find out the large number of variables.
Yeah, so the question was for folks on Zoom that this approach seems to not scale because you have to do a lot of conditional independence tests. So if you have a ton of variables, is this going to be easy to scale up? I will say that somewhat surprisingly, this is a very computationally efficient approach if you make the assumption that the sort of maximum density of your graph is not so high. So the way that people usually, I have results in a couple of slides about the computational complexity of this, but the way that people typically proceed is by saying, if I assume that among all the variables in the graph, the largest number of parents is bounded by some d for every variable, then I can give you a number that bounds the number of conditional independence tests I have to do. So you don't know in advance, of course, how sparse or dense your graph is going to be, but it's sort of not uncommon to assume some sort of degree of sparsity, and then you can get some sort of bounds in the end about the complexity. In the worst case, it is, of course, exponential in the number of tests that you have to do, but that's just the NP hardness of this problem. And I'll add also that in practice, PC and kind of related constraint-based methods are often the ones that scale up the best, in the sense that it's easy to run PC on 5,000 variables. And people do this in genetic applications, for example. Whereas a lot of other algorithms, that's pretty hard to do. And we'll talk about that a bit later too. I think you were next.
So kind of segueing on this, you mentioned the idea of statistical power earlier. And you also just mentioned how in advance, we don't know how many independencies we might need to test along the way. So is there any kind of multiple test adjustment while running all these independence tests? Is there a fear of false kind of positives or false negatives when you're testing for independence?
Yes, for sure. So the good question. So the question was, you're doing multiple tests, and I mentioned something about the power of the tests, but is there some sort of way in which you can keep track of multiple testing adjustments or something similar? So yes and no. Yes, in the sense that there are, so every test, as we're going to see in a couple of slides, like every test will be done with some significance threshold in practice, right? You have some data, you're going to run a conditional independence test, and you're going to reject if it fails to fall below some threshold. So there are procedures so the easiest thing to do would be to say, set that threshold very low as a kind of coarse-grained multiple testing adjustment, so that you do many, many tests, but you're doing them each at a very, very low threshold. So overall, your probability of a type 1 error is small. It's kind of hard to do in this context because you actually don't know ahead of time how many tests you're going to perform. So instead, what people do, you can try and bound the false discovery rate. So like the expected number of false rejections divided by the number of tests that you'll do as a kind of bound, using a kind of loose bound on the number of tests that you'd have to perform for some kind of like density that you're willing to posit. So there are versions of this procedure which sort of adjust that significance threshold in a way to control false discovery rates, for example. In practice, I think it's maybe a little more complicated than that, but yeah. So the question is, can we always assume faithfulness, and what happens if you can't? So the answer is no, you can't always assume faithfulness. I mean, I think these examples that I mentioned earlier about determinism, about exact cancellations, they're all reasons to think that faithfulness is just not universally true. That it doesn't, you don't have to look too hard to find faithfulness violations. But faithfulness is a very useful assumption for learning causal graphs. And so it's pretty ubiquitous, or some version of faithfulness. So, I mean, there's different attitudes to take about that. One is that it's a kind of defeasible methodological assumption, right? So that assume faithfulness until I have some reason to believe that it's violated in this setting is kind of one attitude that people will take. Another attitude people will take is try and come up with algorithms that weaken faithfulness in some way or another. But there are, and to your question about what happens if faithfulness is violated, well, it might be that I remove an edge that shouldn't have been removed, right? So faithfulness allows me to, when I observe a conditional dependence, remove an edge. And if that conditional dependence is actually due to cancellation, exact cancellation, then I've just falsely removed an edge. And that might affect which edges I remove later on in the procedure as well. So it leads you to basically learn the wrong graph. But it'll be wrong in the sense of having too few edges rather than too many. So there are procedures that try and weaken faithfulness in various ways. As we'll maybe get to by the end of this talk, if you weaken your assumptions, you're going to have less strong theoretical guarantees about your conclusions, though. So in terms of like consistency and so forth, you'll sort of run into difficulties there. I think there's a question for
Actually, just a follow-up question on that. I mean, need to not see faithfulness for reasons other than mathematical ones like the direct cancellation. I mean, it just seems like what you're saying when you assume faithfulness is that like the metaphysical reason why you're observing those statistical relations is because there's a causal relation that it maps to. So like aside from the mathematical things, like what does it mean to not assume faithfulness?
So the question is about faithfulness and whether it's a purely mathematical assumption or kind of metaphysical commitment about the causal structure of the system that you're studying. I don't think I view it as a purely mathematical assumption because even though I wrote it,
No, it does seem like it's metaphysical.
Yeah, so ruling out exact cancellations like this, for example, is sort of limiting yourself to like a certain kind of system of study. So, for example, systems that operate under a kind of principle of homeostasis are all around us, and if those ones are likely to violate this kind of assumption, then you're sort of saying, well, I'm not going to perform well in that setting, but I might perform well in a different setting. So it is a kind of substantive assumption, even though I write it down in terms of like the constraints that it puts on the joint distribution, it's something that says that there's some settings in which this procedure will not work well, and other settings in which the procedure will work as advertised. And so if you want a procedure that will work well in those settings in which faithfulness is likely to be violated or thought to be violated, you have to do something else, or weaken faithfulness somehow. And there's like a big literature on like recovering from faithfulness violations. For Frederick, I think you had a hand up there.
Can you go back to the last slide you have displayed? Yeah, so you mentioned here that we cannot find the rotation of all the arrows. Is that because we cannot distinguish between words and paths in this way, or is there any other way you can distinguish?
Yeah, so the question is, like, when we can't distinguish directions, is it because we can't distinguish between forks and chains? Basically, yes. I mean, the idea is that all we know here. So I learned that x3 and x1 are conditionally independent given x4. That could arise because of a chain or because of a fork, right? So that's a sense in which the underdetermination follows from not being able to distinguish substructures. You have to generalize that a little bit to like larger graphs. So there's kind of like d-separations in one direction versus d-separations in another direction that imply the same conditional independence constraints. In the next couple of slides, we'll talk about how you might be able to orient some of the remaining edges using basically logic on the graph that you've already learned. So some additional orientations. The orientations fundamentally all follow from unshielded colliders, but sometimes additional orientations may follow based on the acyclicity constraint, for example. So the fact that I know it's acyclic will lead me to orient an arrow in one way or another. I'll get to that in 1 second. Frederick.
Question from Zoom about whether you can say something about convergence. The question is, what sort of error bound do you get the faithfulness? Is it pointwise or uniform?
I will get to that at the end of this talk.
So I will ask you that as I got it, there is no statistical way to differentiate between the 3 variable fork and the 3 variable chain. Yes or no?
Based on conditional independence without further assumptions, yes. If you want to make further assumptions, for example, parametric assumptions, you can sometimes distinguish between those things. But based on just the conditional independence constraints that are implied, they are observationally equivalent.
Small question, you mentioned it was NP part, doing it as like every language and NP reduces to this, or is it like a more compensated?
Actually, before you answer that, if I could just slip it. What exactly is the problem you're saying is NP hard? What's your input?
Learning the optimal Bayesian network, the optimal directed acyclic graph
From
P of X. It's usually assumed to given P of X.
So P of X is of size.
What is the input?
The input is the distribution, so it's the size P is the number of variables, and
So it's a size 2 to the number of vertices in the graph.
I guess it appears to be binary. Yeah.
Yeah. First minimum. Yeah.
Yeah. So there's the older, I don't remember exactly. I haven't looked at this paper in a long time, but it's like I think it's Meek 1994 or something. It's that Bayesian network learning is NP hard. I think it's binary variables size P.
That paper is not binary variable.
Oh, it's not?
Yeah, it's not. But it's
discrete?
Constant number of values per variable.
Okay, so discrete or categorical variables, yeah, but not continuous.
CHM04.
Yeah. Does that answer the question?
I think so.
Yes.
Just a quick question about the PC algorithm. Does the order of removal matter in which conditional tests to be captures second? Because in practice, maybe some assumptions are violated.
The question is, does the order of tests you do in PC matter? Asymptotically, no, but in practice, yes, right? So in finite samples, because there's a probability that each test will go wrong, then the order in which I test things, because it affects which edges are remaining in the graph, is impactful on the ultimate outcome. And there are, I'm just sort of describing vanilla PC here, but there are modifications of PC that try and reduce that order dependence. PC stable is one way of doing it. And let me put up, so I just gave you kind of like step through of like a simple version of PC, but here's what the algorithm looks like in pseudocode, right? It's relatively short. All it says is that I start from the complete graph over some set of vertices V, or X here. And then I do this loop where S is going to be the size of the conditioning set that I'm going to consider. So I'm going to start with conditioning sets of size 0, meaning marginal independence, and then S equals 1, S equals 2, and so forth. And so for a given size, I'm going to look at pairs of vertices that are adjacent and look at subsets of their adjacencies and test the hypothesis if X1 is independent of Xj given that subset XS according to some given test and significance threshold alpha, and I'm going to go into what that means in a second, but you give me the test, whatever test you want to use for testing conditional independence, and I can run this algorithm by plugging it in. If I find that conditional independence, I'm going to delete the edge, and I'm going to record what set caused me to delete the edge, which is called the sep set, or separating set. And we're going to do this in this kind of loop, increasing the cardinality of the conditioning set. And then when I finish that, I've tested all the conditional independence hypotheses I'm going to test. Then I want to start orienting things. So I'm going to look at every triple of variables, xi, x, k, x, j, that are pairwise adjacent. So where I is adjacent to k, j is adjacent to k, but I is not adjacent to j. So it forms this kind of triple where the two outside ones are not adjacent, but the two inner ones are adjacent. And I'm going to orient them as a collider, an unshielded collider, if and only if the one in the middle is not in the separating set. That's where the unshielded collider rule and faithfulness come in here. And so then that way I'll be orienting a bunch of unshielded colliders, and then finally there'll be remaining undirected edges, and I will apply a small set of rules that that you can show will orient additional edges in a way that just follows by the acyclicity assumption and respects Markov equivalence. Those rules are these four. We can talk about the first couple, to make it clear. So the first rule says that if I see an undirected edge between xj and xk, I can orient it as directed from j to k whenever there's an arrow from I to j such that I and k are non-adjacent. So I'm going to talk about x, j to xk. There's an arrow I into xj such that there's no adjacency between I and k. And so what's the reason? So the rule tells me that this arrow has to go in this direction. What's the reason for that? Otherwise, so the answer is that otherwise I get an immorality or an unshielded collider, right? If I oriented this edge in this direction, then that would be a collider at xj. And so I should have oriented it earlier by the collider rule. So it can't be in this direction, it must go in this direction. It follows from the unshielded collider constraint. Okay. Another one, rule 2, is about cycles. So it says, I'm going to do xi to xj. Whenever there's a path from xi to xk, right? So this rule says that whenever I see this substructure, I have to orient the edge in this direction, because if I oriented it in the other, it would create a cycle. I'll leave in the interest of time, I'll leave the other two to prove to yourself. And they're also just telling you basically preserve unshielded colliders and don't orient any cycles. And the kind of surprising thing about these 4 rules is that it's easy to see that they're sound based on just the kind of argument we just said, but they're also complete in the sense that there's no more orientations you could do besides these 4 in order to orient the CP DAG. Yes.
Is it possible for 2 rules to conflict each other?
The question is it possible for 2 rules to conflict each other? In finite samples, anything is possible, right? Because in finite samples, you can have conflicting conditional independence tests, which lead to graphs that don't really preserve the Markov equivalence class properties, for example. So yeah, in finite samples, you might have to make an order about priority of a lexicographic priority of the rules. But as long as your independence tests are correct, you can never have multiple of these substructures that conflict with correct conditional independence information.
Sorry, can you clarify that? So, any data that you have will be consistent with some graph, perhaps with way too many edges.
So the point is that in finite samples, I'm making a decision about whether to accept or reject a conditional independence. Right? So it might be that there's two conditional independence constraints which are not together consistent with any graph, but I've accepted them both because there's a probability of error for each one. So it's not about the conditional independence as being true or not, it's about whether I've accepted them. Okay, so to summarize the logic of PC, the sort of four main points is that conditional independencies correspond to missing edges. This is the Markov property in faithfulness. The collider rule enables orientation of triples. So that's where most of the arrowhead information comes from. Other orientations follow from basically the acyclicity assumption using those rules or preserving Markov equivalence. And then the remaining unoriented edges reflect the Markov equivalence of models consistent with the data. So it ultimately returns to you a representation of the equivalence class of DAGs, not necessarily a unique DAG. And to go back to the computational complexity point, the kind of classic result is that if you assume bounded degree, so basically that the max number of adjacencies for any vertex in the graph is D, then PC algorithm has a running time that's polynomial in the number of variables. It depends exponentially on the degree. So specifically, the number of tests will be bounded by something that takes like a sum up to D. And then, but if you do start thinking about variations on PC, you might get different complexity results.
So what was P in that slide?
P is the number of variables.
The size, oh, okay. The size of the graph.
The size of B, yeah, or size of X. And then on the consistency side, we're almost at time. So I'm going to come back to some consistency stuff at the end of this slideshow. But the sort of basic, or I don't know, classical results about consistency for PC is firstly thinking in terms of kind of the oracle setting where you have true conditional independence information. So the oracle is this thing which you consult to tell you whether some variables are conditionally independent or not. And you can show that if I have correct conditional independence information, then PC is sound and complete. It returns the true Markov equivalence class, the true CP DAG implied by the true graph G. And then consistency is about what happens as n goes to infinity. And the kind of informal version is that if you assume the distribution is Markov and faithful to some DAG G, and C is the CP DAG implied by G, then as long as I have a consistent test, an asymptotically consistent test of conditional independence, then there's a sequence of alpha values, which I can let shrink to 0, such that in the limit as n goes to infinity, where n is the sample size, the probability of returning the correct graph is equal to 1. There's a somewhat stronger statement that I'm going to get to, I think, on the last couple slides of the slideshow, but I'll return to that a bit later. I'll end here for the break, and we'll come back and talk about this after coffee. But there's a lot to be said about how to test those conditional independence constraints. So in particular, you're always going, in practice with data, you're going to need a procedure, which I called test in my pseudocode, which tests the null hypothesis of conditional independence. You can devise many such procedures, and they'll all look like basically some test statistic, some function of the data will be compared to some sort of significance threshold. And if you reject the null hypothesis, that means you're saying that these things are not independent. So you fail to remove the edge, or you leave the edge in. But if you reject the null hypothesis, then you remove some sort of edge corresponding to this D separation. And after the break, we'll talk about how those tests actually work.
Oh, yeah. Can I ask on the previous slide?
Mm-hmm.
So usually lots of limit statements have like finite sample bounds hidden underneath. Is there like a meaningful like finite sample threshold for alpha n that we get from the proof?
Yeah, so not phrased as in this way, but in the way that I'll talk about later in the presentation, yes. So this is a kind of very weak notion of consistency. It just says eventually you'll get to the truth, the probability one. But for a somewhat stronger thing, which tells you about the rate at which you approach the truth, you need to make somewhat stronger assumptions, which I'll get into in a little bit of time. But yeah, remind me again to answer your question. I think there's a question back there too.
Good question, more high-level question. So if you have an oracle that gives you conditional independences, then you can learn the graph up to Markov. Guessing that you can intervene on your graph, then you can learn the actual graph. Is there anything in between? Are those the two types of operations people reason about?
There is a large space of research in combining observational data with interventional data of various sorts. And I think you'll hear a bit about that on Friday, if I remember correctly.
But it's always those kinds of, like, for example, like remove an edge or add an edge somehow.
Yeah, so the interventional data will typically tell you something about the joint distribution after I've like removed the parents of an edge, right? Because I've forced it to take some particular value. So you can have a combination of that information with conditional independence that you glean from observational data. You might also be thinking of like background knowledge that you might impose that forces some edges to be present or some edges to be absent, or maybe some orientations to be known, kind of a priori on the basis of external information. And all of that can be incorporated into these methods. So I won't go into it here, but if I have information that this edge must be present, or this edge must be absent, or this variable must precede this other variable in the order and it can't go in the other direction, I can incorporate that information at every step of PC. And in fact, that's a great thing to do because it'll do much better in practice if you have such information. So should we break?
Yep, thank you.
Still answer some questions.
So we have a 30-minute break now. There'll be coffee outside, and we reconvene at 11. There'll be a bell. Huh?